Okay, students, let's do some more problems. Let's look now at chapter 22. Okay, so we got chapter 22, problems, page 795 to start with. All right, let's look at problem number 6. Okay, so in a typical lightning strike, 2.5 coulombs flows from the cloud to the ground in 20 microseconds. Excuse me, not micro, milliseconds. What is the current during the strike? Okay, so we've got a storm cloud here, and so we get a lightning bolt that comes to the ground, all right, and the charge in the lightning bolt is 2.5 coulombs of charge. And this occurs during a time interval of 20 milliseconds, okay, which is 10 to the negative third seconds, okay? So we want to know what the current is. Wow, okay. Well, if we go back to the original definition of current, and if you took my calculus class, you would see that current is actually the derivative of the charge with respect to time, okay? It's actually a derivative because it's the rate of change of charge during a time interval, okay? But since we're looking at it here not using derivatives, we're not looking at it through taking a derivative. We're just looking at if the situation was a constant situation, we're just going to look at the change in charge over the change in time. So this becomes a real easy application, okay? So current then would be equal to what? We want to know what's the current. Oop, I didn't write that down. So what is the current during this time interval? Well, we say then the current is equal to 2.5 coulombs divided by 20 milliseconds. And what do we get? Well, we get 2.5 divided by 20 to the negative third. And we shouldn't get a math error. If I could punch a calculator, I would be dangerous. We get, what did I write? What did I do wrong? Oh, I wrote 20 milliseconds instead of 0.2 milliseconds. I'm sorry, y'all. Okay. It's 0.2 milliseconds. There we go. Y'all probably caught that, didn't you? I hope you did. Oh, it's been a long day. All right, so it's 0.2 milliseconds. Now we're doing it right. So we got 2.5 divided by 2 to the negative fourth, or 0.2 to the negative third, and we get 12,500, or we'll say 1.2.25 times 10 to the what? Fourth amps, because coulombs per second is an amp. Okay? Now, looking at the number of significant figures, that would actually round to 1.3. Okay? But, or you could say 1.3 times 10 to the fourth amps. Or that would be what? 13 kiloamps? Yeah, 13 kiloamps, if you were to write it that way, okay? You could write it using the prefixes, okay? All right, and that is a large amount of current, and of course that would be expected with a strike of lightning. That's why it kills people, okay? All right, let's move on now. Next problem. All right, next problem is number 15. Number 15 is on page 796, okay? All right, so we have what? All right, so we have a 9-volt battery supplies 2.5 milliamps of current to a circuit for 5 hours. So let's just say we got a battery here. Okay, there's our battery. And we got, I don't know, let's just make a light bulb, okay? Or let me do it this way. Hang on. Let me draw it this way. All right, so we got a battery and we got just a resistor here. All right, and it comes around. And let's see. The 9-volt battery voltage is 9 volts. Okay, 9 volts right here. All right. And it supplies, the current is 2.5 milliamps, okay, of current for 5 hours. And the time interval is 5 hours. How many seconds would that be? That would be, well, 1 hour is 3,600 seconds, so 5 times that would be what? So 5 hours times 3,600 is 18,000. I had to calculate that. That would be 18,000 seconds, okay, right? 5 times 3,600, yeah, because 60 times 60 is 3,600, all right? So it'll be 18,000 seconds, all right? How much charge has been transferred from the negative to the positive terminal, all right? We want to know how much charge has been transferred, okay? Well, here again, we know that current, by definition, is the rate of charge, right? It's the amount of charge during a given time interval. And it actually gets a little bit more complex than that. When we look at how we derive current and even Ohm's law is a very simple equation, but it is one more derivation. Because what the heck is an ohm, okay? You know, we can understand, coulombs are, you know, charge is pretty easy to understand, and voltage is pretty easy to understand, but what the heck is an ohm, okay? And so when you look at these derivations, current is a little more complex too, because you look at the drift velocity, you look at the number of charges, you look at the length, you know, there's several things that come into play there, okay? All right, and we get into that in our Cal-based class. Now, so current is equal to the change in voltage to the time interval, so we can find what? We can also find then how much charge, and that was what? how much charge has been transferred. So A is Q. We want to know how much Q, okay? All right. So we know from this equation, we also know from electric potential energy, we can find what? The charge times the change in voltage. We can also do it that way if we had to do it, all right? So let's look at how much charge is transferred, all right? So if we take this equation right here and solve for Q, so then delta Q is equal to what? The current times the change in, the change in time. And so let's plug everything in. We've got 2.5 milliamps of current times, and I'm going to put that in seconds, so that's 1.8 times 10 to the 4th seconds, right? 1.8 times 10 to the 4th seconds, okay? And let's see what we get. And you say, why did you put it in seconds? Because you got to remember, what are amps? Amps are the number of coulombs per second, not coulombs per hour. So we have to make sure we keep our units. We got to keep the right units, okay? Don't forget that, all right? So we got 2.5 to the negative third times 1.8 to the 4th, and we get 45 coulombs. That's a 4, believe it or not, 45 coulombs of charge, because everything cancels out. Amp is coulomb per second, so the coulombs cancel out. Coulombs per second, the seconds cancel out, and you're left with coulombs, okay? So that's A. Now let's look at B, okay? So what was this, number 15? Yeah, 15B. I almost forgot where I was. 15B says how much electric potential energy has been gained by the charges that pass through the battery. So we're looking for electric potential energy, and remember that's Q times the change in voltage, right? So we're finding the how much electric potential energy has been gained, okay? All right, so then we can say it this way too, and that's electric, that's an E by the way, is equal to the charge, which is 45 coulombs, which is a lot, times the change in voltage, which is 9 volts. And so we get a delta. If my pen doesn't quit doing that, that's electric potential energy, is equal to what? So we got 45 times 9, so we got 45 times 9, and we get what? We get 405 joules. So we get 405 joules of electric potential energy, okay? All right. 405 joules electric potential energy. All right, let's look at number 18 now. I'm going to go to a clean slide. Okay, so number 18. All right, we have a wire with a resistance R is connected to the terminals of a 6-volt battery. All right, so we got a 6-volt battery here. The battery has a voltage of 6 volts. And we got a wire. All right, here's the positive, there's a negative. Okay, and the wire is connected. So we're just going to do this. We're going to come all the way around. We're going to make a nice little fancy trip here to here, okay, there to there. So they're connected, okay. All right, now, well, they're really not touching, are they? I need to make it touch. Let's do it this way. Let's do it this way. Let's make like a D-cell battery. So here's our D-cell battery. Okay. All right, so we got a wire that comes and does this right here. There we go. And let this be the positive, that's the negative. Okay? All right, now make everybody happy maybe. And the voltage of this battery is 6 volts. All right, so it's touching. Now, it says a wire with resistance R, and then it says what is the potential difference at the ends between the ends of the wire and the current if the wire has the following resistance. Okay? So we want to know what is the potential difference. So we want to know what delta V is in the ends of the wire, or the wire, okay, question mark, based on these different resistances. So if R is equal to 1 ohm, what is delta V? Well, how do we find this, y'all? This is a simple Ohm's law problem, all right? By the way, did it give us current, 6-volt battery, and the current I through the wire has the following resistances. Did it not tell us the current? Well, what am I looking at here wrong? All right, we're going to find the change. We got the change in voltage. Oh, we're looking for the current. I'm sorry, not the voltage. It says, all right, what is the potential difference ends between the ends of the wire and the current I through the wire if the wire has a following resistance? Okay, so yeah, duh, I'm crazy. Well, we know what the potential difference is, y'all. That's not going to change. All right, that's 6 volts. I was misreading the problem. All right. You say, how do you know? Well, because from here to here it's 6 volts. It has to be 6 volts. Okay. All right. Because that's the voltage of the battery. Now, so what is the current? Okay. So what is the current based on different ohmages of the wire? All right. So if you have a 1 ohm, well, we know that V is equal to IR. That's Ohm's law. And I is equal to the voltage divided by the resistance. So then the current for a 1 ohm is equal to 6 volts over what? 1 ohm. And that is what? 6 amps. Boy, that was hard, wasn't it? B, all right, what is it for B? B is 2 ohms, all right? Well, we know that. So if it's 2 ohms, all right, so the current for the 2 is equal to 6 volts divided by 2, which is what? 3 amps, right? Okay. And then for C, it is 3 ohms. So the resistance is 3 ohms. All right, so we plug everything in. The I for the 3 is equal to what? 6 volts over 3 ohms is equal to 2 amps. That's real hard, isn't it? Okay, that's a real simple problem, okay? So that's all you have to do there. Just a simple Ohm's law problem, okay? All right, let's move on. Let's look now at number 23, and then after this one we got a couple of more, okay? So number 23, and that was on page 790. By the way, I've already told you what page. On number 23, which is on page 796. Okay. It says a motorcyclist is making an electric. Hang on a minute, y'all. I've got to get this call. This is my dad's doctor. Okay, sorry for that little quick, brief interruption. I had to get that. It's my dad's doctor. Okay. All right, so we got a motorcycle is making an electric vest that is connected to the motorcycle. Excuse me. Excuse me, I'm sorry. To the 12-volt battery. So he's got a vest. I'm just going to draw something like this. And here's our battery. Okay. positive, negative, and so it's connected, all right? And the voltage in the battery is 12 volts, all right? And it says, we'll warm her on cold days. She is using a 0.25 millimeter diameter copper wire. And so the wire in this thing, okay, the wire has a diameter, and it is copper, and the diameter of the wire is what? 0.25 millimeters, which is 0.25 to the negative third meters. Okay? All right. And she wants a current of 4 amps in the wire. So the current in the wire is 4 amps. Okay? And by the way, that's the diameter of the wire. Diameter of the wire, which is copper. D of the wire is copper. All right? 4 amps in the wire. What length wire must she use? Okay? So how long does the wire have to be? Well, we know from Ohm's law that V is equal to IR, and we also know that if we have a material and we want to calculate the resistance in it, and by the way, these are the equations, equation 22.8 is Ohm's law, and then the resistivity equation, I can't remember exactly, that might be the, let me just look real quick, that might be the same equation, 22.8. Equation 22.8, 22.7, yeah, 22.7 is that one, and 22.8 I believe is Ohm's law, yeah, 22.8, yeah, okay? So 22.7 is this equation. So this equation, to find the resistance in a material, whether it's a wire or whatever, is equal to the resistivity of the wire, okay, times the length of the wire divided by the area of the wire, okay? So to find the resistance of a wire, we take the resistivity, and that is a constant, and every material has a particular resistivity, and this table is on page 782, table 22.1, all right? So we want to find what length of wire is required for that to work properly, right? Well, first of all, we need to do what? Okay, we need to find what? Let's do some combinations here. Let's do some substitutions, okay? All right, so we got to find, so we got the voltage, we've got the current, okay? So we know then that R is equal to what? R is equal to the voltage divided by the what? By the current, isn't it? Okay? The voltage divided by the current. Now watch what I'm fixed to do. If we come over here and substitute right here, we say the voltage divided by the current is equal to what? The resistivity, rho, times the length of the wire times the area. So now let's find the length of the wire. Find out what length of the wire it is. So the length of the wire is equal to what? Well, that's going to be the voltage times the current times the resistivity, the voltage times the area divided by the current times the resistivity, okay? All right, now you say, well, what is the area? Well, since this is a wire, the area of a wire is pi r squared, right? Okay, so it gave us the dimensions there. The diameter was 0.25, so the radius of the wire would be what? 0.125, yeah. 0.125 millimeters, because 0.125 times 2 is what? 0.25, right? So we got to use the radius of the wire. So this one takes a little bit of thinking. So let's start plugging in. So the voltage was what? 12 volts, okay, times the area, which is pi r squared. R was what? 0.125 meters. Whoa, 0.125 to the negative third meters. Boy, I about messed up. Sorry about that. Times 10 to the negative third meters squared divided by the current, which is 4 amps, times the resistivity. And if you look on page 782, table 22.1, that is 1.7 to the 1.7 times 10 to the negative 8 That's 1.7 times 10 to the negative 8th ohm meters, okay? Okay, so now let's do the calculations, all right? So you see how I solved for this equation right here? You see how we solved for it? We had two equations, and we plugged them together and solved for the length, okay? Do you see how we got to that? All right, I hope so. All right, so what do we get here? Let's do a little calculation here. So we got, I'm going to do the radius first since it's squared. So we got 0.125 to the negative third. Okay, yeah, 0.125 to the negative third squared times pi, and you do need to use pi on your calculator, times 12 equals, divided by 4 times 1.7 to the negative 8, that's your resistivity constant. I put all that in parentheses, is equal to, and we get 8.66, so I get 8.66 meters, or you could just round it and say 8.7 meters, okay? There we go, that's the length of the wire. That's a good problem right there, because that's combining equations. I like problems like that, okay? All right, so that's number 23. Now let's look, we've got a couple more, number 33 and number 37, and we'll be done for the day. So number 33 is on page 797, okay? And number 33 says what? Okay, so it says a copper wire is 1 millimeter in diameter and carries a current of 20 amps. So we got a copper wire, okay, and that's a copper wire. I'm going to use the periodic table symbol for copper wire. And it is 1 millimeter. The diameter is 1 millimeter, giving it a radius of what? 0.5 millimeters, which is 10 to the negative third meters, okay? And it has a current of 20 amps. That's pretty high current, isn't it? Okay. What is the electric field inside this wire? Okay. All right. Well, we know Ohm's law, V is equal to IR. Okay. We remember that. And then if we go back and we tie in our equations, we also remember from the electric field chapter that what? The change in voltage over the what? This can be D or L. Actually, when I teach it in my calculus-based physics class, we'll say delta X, but we're going to put L since it gave us a, did it give us a length of wire? Did I misread this? 1 millimeter carries a current. Yeah, okay. So it didn't give us the length of wire, but it gave us the diameter of the wire, okay? Which is okay, all right? Because you say, well, why is that okay? Well, I'm going to show you, all right? So V is equal to IR, all right? So let's do some substituting. Let's substitute this right here. You say, where'd you get this right here? We got that from our electric field equation. One way to find an electric field in an electrical device, especially a capacitor, is the change in voltage divided by the length of, or the distance between the capacitor plates, or the length that we're measuring the change in voltage, the distance from the source, okay? All right, so let's do some substitution. So then that becomes what? Electric field is equal to IR over what? L. And you say, we don't have a length. Well, just hang on. All right, now how do we find resistance of a material? It's rho times the length divided by the area, right? You say, where's that from? Whoop, go back right here. Go back right there. Right there it is, okay, all right. Okay, so now let's plug that in, and so now we've got the current times what? Well, it's the rho times the length over the area divided by the length. Now look at there, we got a complex fraction. And so if you bring that up, let's go one more step, and so we've got the current times rho times what? The length over the area. Now look, I'm going to bring this, that's a complex fraction, so watch, times 1 over L. Watch now. Cancel, cancel. And what are we left with? We're left with then what? The electric field is equal to the current times what? Rho over the area, right? Everybody concur? Yes, we concur. All right. So let's plug everything in now. So the current was 20 amps, okay? The resistivity of the copper, we've already done that, 1.7 times 10 to the negative 8 ohms per ohm meters, divided by the area. Well, that's pi r squared. By the way, I didn't write that. The area of a wire, because it's round, is pi r squared. So we got pi, and you do use pi, and we got 0.5 times 10 to the negative third meters squared. And so what do we get for an electric field? All right, well, let's just see real quick. Let me make sure I got my calculations right. So we got 20 times 1.7 to the negative 8, okay, equals, divided by, all right, we got pi, and you use pi on your calculator, times what? 0.5 to the negative third squared. And what do we get? We get 0.43 newtons per coulomb, or volts per meter. Now, which one would be more practical? Well, actually, it would be a little bit more practical that we use volts per meter, okay? All right, because remember, look, your meters cancel out right here. Well, I say they cancel out. You got, this is a meter squared. An amp times an ohm is a volt. Amps times ohm is a volt. Look right here. So let's use volts per meter, because look, an amp times an ohm is a volt. Meter squared over metered, well, guess what? This meter cancels out and the meter on the bottom's left, so volts per meter is the actual unit we should use. Could we say newtons per coulomb? Yes, we could. But we use the units that we are given, okay? And in this problem, it was volts per meter, all right? Okay, I hope that helps on that problem. Let's look at one more. Boy, it's been a long day on this one. All right, number 37 is the last problem. Same page, page 797, okay? Page 797, all right? All right, one more. I know about you, but I'm tired. All right. Okay, been a busy week. All right. So we've got what? We've got a 1.5 D-size battery stores 54 kilojoules of energy. So we got a D-size battery here. All right. And it stores, its electric potential energy is what? By the way, it's a 1.5. The voltage is 1.5 volts, okay? And it has an electric potential, stores an electric potential of 54 kilojoules, which is 10 to the third joules, 54 times 10 to the third joules. What steady current could this battery provide for 20 hours before being depleted? So we want to know the current, okay, for 20 hours before being depleted. The current for 20 hours. How much current would it provide, okay? All right, well, this is actually a power equation, all right? It really is. And you say, well, how is that the case? All right, now look, y'all. If we look at equation 22.13, we know that power, and there's actually three equations for current. Power is equal to what? The current times the change in voltage, right? That's delta V. Boy, I can't write. Let's do this again. Whoop. Delta V. So current power is equal to current times delta V. And we also know by definition that power from mechanics was what? The work divided by the change in time. Well, what is the work? Well, it's the potential electric energy divided by the change in time, right? We know that from, because look, y'all, power is power. You say, we did that back in mechanics in 201. Yes, you sure did. Or 202, okay, whichever, 201, excuse me. All right, yes, you sure did back in the first semester of physics, okay? Well, look, work and electric potential is the same thing because the units are joules, okay? So we want to find out what? We want to find out how much current, right? Right, okay? So then we can say this, power and power. All right, look, this is power and that's power, so set them equal to each other. So current times change in voltage is equal to what? The change in electric potential energy divided by the change in time. And so then the current would be equal to what? The electric potential energy times the change in time times the change in voltage, correct? Yes, that is exactly right. Now, what do we got to do with our time here? We've got to convert 20 hours to seconds. So how do we do that? Well, okay, look. 1 hour is equal to 3,600 seconds, right? So 20 hours, let's do a dimensional analysis here. That's an H, by the way. That looks like a K, doesn't it? No, it's an hour. It's an H. There we go. And we know that 1 hour is 3,600 seconds. So cancel that out. So what does that equal? So 20 times 3,600, that's a big number, isn't it? Times 3,600. And we get 7.2 to the 4th seconds. So 7.7 stars. Let me try this again. 7.2 times 10 to the 4th seconds. Okay, that's a point. 7.2. 72,000 seconds, or 7.2 to the 4th. All right? So let's plug everything in. Here we go. We're almost done. So current is equal to, the electric potential was what? 54 kilojoules. So that's 54 times 10 to the 3rd joules. You got to learn these prefixes, y'all. The time was 7.2 times 10 to the 4th seconds. All right. Times what? The change in voltage was 1.5 volts. And so what do we get? All right, so we got 54 to the 3rd divided by 7.2 to the 4th times 1.5. And we get an awesome number of what? 0.5 amps. There you go. All right. Okay, I hope these problem sessions help.